Hi, and welcome to this section of the Algebra word problem tutor. And in this section, we're going to do problems dealing with levers. Okay, lever is a fancy word that just means some kind of flat surface with a pivot point. That's a lever, something like this, like a seesaw. Okay, so the good news is these are going to be word problems, that you have some experience with because we've all gone to the playground, we've all done the seesaw. So you're going to have people sitting on the left, people sitting on the right, and you have some experience with doing this already. You have some experience with playing on the seesaw. So I think you all know that on a seesaw, if this is the seesaw here, if I put a person here on one end and a person on the other end, if we're both exactly the same amount of weight, okay, then the seesaw will be perfectly balanced, right? And I think you also know, just intuitively from playing on the playground, that if you have a really heavy person, let's say you have a really light person, like a baby, okay, like a toddler. You take your toddler to the park or something, and you put him on one end. He's really light, okay? Now, if you're an adult and you sit on the other end, then you're going to just sit all the way on the ground, and that toddler's going to go up in the air. So in order to balance the seesaw, you know from your playing on these things that the adult can move on in towards the pivot point. And eventually, if you get close enough to the pivot point, you can still balance the seesaw, okay? So these problems are going to deal with that. They're going to be dealing with people sitting different distances and stuff from the edge of the seesaw, and we're going to talk about how to do that. So before we actually get into the word problem, let me teach you a little bit about levers, okay? So you have something called a basic lever, okay? It's a seesaw. I mean, it's just a fancy word that means seesaw. So here's this middle point where you're balanced here, okay? This thing has a special name. It's called a fulcrum, okay? Don't worry too much about the name. The only reason I'm even telling you the name is because the word problems probably are going to use the word fulcrum. It just means pivot point. It's a fancy word that means pivot point. It's nothing special, okay? And you have a person over here. I'm just going to put it as him as a box, but it could be a person, okay? A big box, let's say. And he has some weight, okay? I'm going to call him weight 2 because he's box number 2, let's say. And then you have a little smaller box over here, and I'm going to say that he is weight 1 because he's box number 1, he is weight 1. So you have two boxes, different weights, okay? Now, also, there could be different positions on this thing, just like you can play different positions on the seesaw. So this distance between box number 1 and the fulcrum is just called L1, and this distance here from here to the other box is L2. So you see, it's a fancy looking drawing, but really you have this seesaw and you have this fulcrum where it's pivoting. You have person number 1 or box 1, a distance L1 from the fulcrum, and you have another box with a different weight, weight 2, that's a different distance, okay? Now, here's where the magic comes in. Really, it's physics that comes in here. This seesaw is balanced, okay, when the following is true. The distance 1 times the weight 1 is equal to the distance 2 times the weight 2. Okay, this seesaw is balanced in that condition. Okay, so what this is saying is that when the product or the multiplication of the distance times the weight on the left is equal to the distance and times the weight on the right, if these two products are equal to each other, then the seesaw is balanced. Okay. Now you can kind of get a sense of that because what I was telling you before is that when you go to the park, if you have a toddler on one end and an adult on the other, we obviously have different weights, right? The weight of the toddler is going to be totally different than the weight of the adult. Totally different. So if this is the toddler, let's say, and his weight is, let's say 10 pounds. Well, that's not a toddler, that's a baby. Let's say the toddler is 25 pounds, okay? That's his weight. He's sitting on one side. And let's say the adult weighs, let's say 200 pounds, okay? Well, if this seesaw is going to balance, there's no hope for the seesaw to balance without playing with things here because this is only 25. This is only 200. You've got to do something to make it balance. So let's say the distance L1 of the toddler from the fulcrum, the distance from the fulcrum, let's say he was sitting, let's say it's 10 feet. Let's say he was sitting 10 feet from the fulcrum, 10 feet, okay? So then 10 times 25 will give me 250, okay, 250. Then I would have to choose L2 so that I could choose L2 times this 200 to also give me 250. And the only way that's going to happen is if L2 is going to be much less than 10, okay? So what it was saying is the same thing as true before. The big, heavy adult, if they're going to balance the seesaw, is going to have to move closer to the fulcrum. It's the same thing here in math. You have a very light person sitting some distance away, a heavy person sitting. You can't put him sitting 10 feet away. He will not work if you put him 10 feet away, because 10 times 25 is 250, 10 times 200 is 2,000. These two are not balanced in that case. You can't pick him, you can't put him 1 foot away, okay? Because if you put him 1 foot away, he'll be 1 times 200 is 200, and this on this side is 250, but we're getting closer, so it's 1 point something. You put him 1 point something feet away from the fulcrum, very close to the fulcrum here, and then he can balance. So that's kind of an aside, okay? The main thing is here, this is how a seesaw balances. This is all the magic of a seesaw here, of a lever, okay? So let's go ahead and work the first problem. It says, John weighs 80 pounds, and he sits 4 feet from the fulcrum of a seesaw. If Sally weighs 100 pounds, and how far from the fulcrum should she sit to balance the seesaw? So, first, always going to draw a picture when it comes to these kinds of problems, because I just think it's just so much better, and you can really visualize what's going on. So here's the seesaw, okay? Now let's go ahead and put somebody over here. This is this person here, and it's 80 pounds, okay? So this is John, who weighs 80 pounds, okay? And it says right here he sits a distance of 4 feet from the fulcrum. Okay, now there's another person right here that weighs 100 pounds. Okay? The question is, how far from the fulcrum should he sit in order to balance the seesaw? So we have to know right away that this person is going to be sitting some distance L2 away from the fulcrum. This is person 1, this is person 2, so I'm calling him L2. So our equation for balance of a seesaw is simple. Okay, so what we do is we write down the equation that we have to balance, and we just plug in what we know. This guy is sitting 4 feet from the fulcrum, and he weighs 80 pounds, okay? And this guy is an unknown distance here, and he weighs 100 pounds. So we just solve this equation for L2. 4 times 80 is 320, and then this is 100L stays the same. And then to solve for L2, we just divide both sides by 100. 320 divided by 100 gives us 3.2 feet. And you really need to look and try to check your work at this, because this is kind of a problem that you have some experience with. You should at least try to see if it makes sense. We know that if this person weighed 80 pounds, he would be exactly the same weight as this person, and then in order to balance the seesaw, they would have to sit exactly the same distance apart on the seesaw if they weighed the same. But he doesn't weigh the same, he weighs more. So if we put him at 4 feet and he weighs more, then that seesaw is going to teeter. Okay, we know this because just from our everyday experience. He weighs more. If you put him equal distances, seesaw is going to move. Okay, so he weighs more. That's going to happen. The only way you can counter that from your experience on the playground is for him to move closer to the fulcrum. Then we can get the seesaw to balance. So that makes sense with what we calculated here. Instead of 4 feet from the fulcrum, he's sitting a little bit closer, 3.2 feet. Okay, the next problem we have says, at one end of a lever, there's a 10-pound weight, which is 8 inches from the fulcrum. How much weight should be placed on the other end, 20 inches from the fulcrum, to balance the lever? Okay. So again, it's the same thing as before. We need to draw a problem. We need to draw a picture to see what we're talking about here. You really cannot start these problems without drawing a picture. So what we know is it says at one end of a lever there is a 10-pound weight. 10 pounds weight, okay? And that's W1, we'll say. Okay, and we know that he is 8 inches from the fulcrum. Okay, now we also know that there's another weight over here we're going to call W2. I don't know how much he weighs, but I do know that he is 20 inches from the fulcrum. Okay, and I know that because the problem says exactly this. At one end of a lever there's a 10-pound weight, which is 8 inches from the fulcrum. How much weight should be placed on the other end, 20 inches from the fulcrum, to balance the lever? So our balance condition is L1 times weight 1 is equal to L2 times weight 2. Very simple, okay? L1 is 8 times the weight 1 is 10 is equal to L2, which is actually 20, we know what that is, times the weight 2, which is something we don't know. So we're using our balance condition here. 8 times 10 gives us 80 is equal to 20 W2, and in order to solve for W2, we just divide both sides by 20. Okay, and so then W2 is just simply going to equal 4, and that's 4 inches. I'm sorry, 4 pounds. Okay, 4 pounds. So again, you want to see if this makes any sense at all. Okay, again, you know that this is 10 pounds 8 inches from the fulcrum. If this weight weighed 10 pounds, exactly the same as this one, then you know he would have to be at 8 inches. Okay, you know he would have to be here because if you have equal weights on the same distance from the fulcrum, they'll balance. Okay, but he doesn't weigh. We're claiming he doesn't weigh 10 pounds. We're claiming he weighs 4 pounds. So let's see if this makes sense. So he's super light. Here's really light and here's heavy. Okay, and you know that if you put him 8 inches from the fulcrum and he's lighter, then this seesaw is going to teeter this way. And you know the only way to counter that is to get him to move real far out. Okay, so he is sitting farther away, and that's exactly what the problem shows right there. So we're just trying to make sure it's consistent. We're trying to make sure it makes sense. If he's lighter, he must sit farther away. You have to run it through your sanity check. Just the same way if you were calculating the age of a person and you got a negative 10 years, you go, that's not right. Something's not right with this problem. Or if you're calculating the distance to the moon, okay, and you're doing a long calculation of the distance to the moon, you got negative 10,000 miles. Holy moly, that's not right. Negative numbers can't have negative distance, at least not when you're talking about going to the moon, because you know that's out there and that you're not going to be going negative to get to the moon. Okay, so next problem. A person places a lever under a 60-pound rock that is 3 foot from the fulcrum. How much pressure, or how much force, in pounds must the person place on the other end of the lever if he is 5 feet from the fulcrum if he would like to move the rock? Okay, so let's say that one more time. A person places a lever under a 60-pound rock. So you have this rock on the ground. It's really heavy. You want to move it. Okay, he puts the lever under a 60-pound rock, and he puts a fulcrum in there that's 3 foot from the rock. How much force in pounds must the person place on the other end of the lever, pulling down on the thing, to move the rock if he is 5 feet from the fulcrum? So that's what we're trying to find out. So you have a picture that roughly looks something like this. You have this rock over here. It's really heavy. You want to move it. He has a weight of 60 pounds. Okay, and then you have this lever, which is just could be a big board or something, and you want to move this rock. So you put some kind of fulcrum underneath here, some kind of pivot point to help you move this rock. And what you plan to do is you plan to grab it and kind of pull on it, okay? And the problem tells you that this rock is 3 feet from the fulcrum, and it also tells you that the person pulling down is 5 feet from the fulcrum. Okay? The question is, how much force do you have to pull down to get the rock to move? This is actually very practical because, a lot of times this is exactly what you're doing. You're doing something kind of similar to this when you jack up a car. I mean, how do you think you can actually push something with your hand to lift a car? I mean, there's a lever involved in that in a lot of cases. And in fact, you ever heard the old saying, really old saying, if you give me a lever big enough, I shall move the world, okay? Right? Well, the theory goes that you can lift anything if you have a big enough lever because it lets you have some mechanical advantage to your work there, okay? But it's a simple lever. You have somebody standing 5 feet over here, 3 foot here, and you're going to pull down and move this rock. But in the end, it's just a seesaw kind of turned sideways, really. So the balance condition is L1 times W1 is got to equal to L2 W2. Now I'm applying, you might say, well, how can you apply this? This isn't a seesaw. Well, what I'm trying to say is, if I start pulling on this thing, okay, I'm going to pull and pull and pull. The wood is going to bow and bow and bow. Eventually, I'm going to pull so hard that this rock is going to begin to move. Okay, I think you all agree with that. What I'm trying to say is, at the moment that it begins to move, it's almost like a seesaw then. It's like I've exerted enough force to get him to begin to move. So I've just moved beyond balancing. Okay, I moved into actually moving them. So this condition here is really talking about the point right at which the rock begins to move. Okay, right at the point where it's not really bounced anymore, when the rock starts to move. So that's why we're using that. So if I'm going to pull down with a force of W1, then you would write it like this. L1 is 5, W1 is what I'm trying to solve for, is equal to L2 is 3 and W2 is 60. Okay? So then 5W1 is equal to 6 times 3 is 180. 60 times 3 is 180. So then W1 is equal to 180 divided by 5. So W1 is equal to 36 pounds. Okay? Now, just think about this for a second. 60-pound rock only took you 36 pounds to move it. That's pretty cool, right? But how did you do that? How is that possible? I'm going to give you a little physics lesson here. How can this be done? You don't get something for nothing in the world, okay? And it's true here. It looks like you did get something for nothing. It only takes you 36 pounds to move a 60-pound rock. That looks pretty cool. That looks like getting something for nothing. But when you think about it, in order to do this, you have to pull this lever an awfully long ways, okay? In other words, I have to pull that lever through a long distance. I don't have to pull very hard, but I have to pull it through a very long distance in order to get that rock to move a very short distance. This rock's just going to kind of move a little bit, and my arms pulling down are going to move a very long distance. So it's a trade-off. I'm trading the force I need to use for the distance I need to pull through. And that's a good trade because it's easy for me to pull at 36 pounds. And if I make this lever farther and farther and longer and longer and longer, if I make this lever 100 miles long, okay, then I don't have to pull very hard at all. I'm going to have to pull very, very gently. But I'm going to have to pull it a long way to get it to do anything, okay? Okay, the next problem says, where should the fulcrum be placed under a 6-foot lever if there's a 24-pound weight on one end and a 36-pound weight on the other end in order to balance the weight, or in order to balance the seesaw, okay? So what we have here is, same thing, just draw a picture. What we have here is, on one end, we have a 24-pound weight, okay? And I'm going to go ahead and draw this like this. On the other end, we have a 36-pound weight. Okay, and you have some fulcrum somewhere, but I'm going to draw it like a dotted line because we don't know where we're placing it. That's sort of the problem. Notice the problem says, where should the fulcrum be placed under a 6-foot lever? So that's the first thing. We know this is 6 foot long. Okay, we know this is 6 feet long, right? There. And where should we put it? Should we put it here? Should we put it here? Should we put it way over on one side? Where do we put it in order to balance it? Okay. But the same thing applies. It's L1 times W1 is equal to L2 times W2. Well, you might ask yourself, well, I don't know what L1 and L2 are. All I know are what the weights are. Well, that's true, but don't forget that you can define things in your drawings. This is L1. However far you choose it to be, that's L1. And this is L2. Okay? So if I put the fulcrum here, this is L1 and this is L2. If I put the fulcrum over here, then this would be L1 and this would be L2. But wherever you put it, the distance between the fulcrum and this is L1 and this is L2. Okay? Now here is where the magic lies. You look at this and you might say, well, I haven't really made any progress. I still don't know what L1 and L2 are. But the magic thing they gave you is that you had a 6-foot lever, okay? So that means that whatever L1 is, L1 plus L2 must equal 6. Because this distance plus this distance, no matter where I put the fulcrum, if it's a shorter L1 or a longer L1, the sum of those two things must be equal to the length of the lever. Okay, so the first thing I want to do is solve this equation over here for one of these things. I'm going to pick L2 is equal to 6 minus L1. Just subtract L1 from both sides. And then I'm going to plug it right back into here. So L1 times W1, which I know, I can put the number in there now, it's 24, is equal to L2, which I know now is 6 minus L1 times W2, which is 36. Okay? So now I have an equation that only has L1 in it, and that's a good thing. 24L1 is equal to 6 times 36, just distributing in there, is 216 minus 36L1. Okay? So all I did was distribute the 36 in. 6 times 36, 216. 36 times negative L1 gives me this. Now let's move this over to the left to combine this. So let's add 36L1 to both sides. All I did was add 36L1 to here, gets rid of it, add it to this side. Okay, so then when I do that, I'm going to be left with 60. L1 is equal to 216, so then L1 is 216 divided by 60. L1 is going to be equal to 3.6 feet. So this distance is 3.6 feet there. So what that actually tells you where the fulcrum must be. We've drawn our picture in such a way that L1 is defined as the distance between the 24-pound guy and the fulcrum. So this L1 tells us precisely what the problem asked, which is where do we put this fulcrum. You would write down in your paper, we put the fulcrum 3.6 feet from the 24-pound person. Then this seesaw will balance.